hi everyone, my name is Imtiaz and I'm here with my partner Alrawi. We both are going to help you tackle the chapter Enzymes, which honestly it's a really easy chapter with just a little bit of memorization and understanding. These questions are going to be one of those that you're going to answer instantly in your final exam, okay? And so I'm going to be covering 6.1, 2 and 3. Farouk will do 6.4 and 5. And my part is mostly question and answers, so I want you guys to interact and brainstorm whatever you know. Then we'll discuss, have a discussion, and I'll display the answer, and I'll tell you what are the key terms that you're missing out. Okay? Sounds good? So let's start. First of all, what are enzymes? If I were to ask you to define an enzyme, how would you define it?
Catalyst to speed up metabolic reactions.
English, I don't understand Arabic.
Yeah, I just said.
Oh, you said it in English?
Catalysts that speed up reactions.
Yes, exactly. So they're biological catalysts. What is the composition of an enzyme? Are they made up of carbohydrates?
Proteins.
Proteins. Are all enzymes made up of proteins? Yes? No? No. Exactly. Yes, exactly. They're made up of RNA. Some of them are made up of RNA, and those are called ribozymes, okay? Most of them are proteins, but there are some that are RNA, okay? And since we said it's proteins, are they in the, what form are they present in? Is it quaternary, tertiary? Exactly, perfect. And the enzymes that the reactions that they're catalyzing, are they gonna change while catalyzing the reaction?
No, they don't change.
They won't change, exactly. And will they form side products? No. Yes. They will not form side products. And enzymes will increase the rate of chemical reaction, as we mentioned. How are they increasing the rate of chemical reaction?
Stabilizing the transition state.
Okay, a more basic answer?
Decreasing activation energy.
Yes, decreasing activation energy by choosing a pathway, alternative pathway that requires less energy. Exactly. And so, why am I taking a further step to use an enzyme? I might as well just increase the temperature or increase the concentration. Why am I using an enzyme? Why can I not raise the temperature? Sorry?
Biological conditions.
Okay, what are the biological conditions? If I raise it, what will it lead to?
Denaturization.
Denaturization, exactly. And for my reactant concentration, I cannot raise it because in nature, the reactant concentrations are low. That's why the most ideal method is to use an enzyme. Okay? So like we discussed, all enzymes are not proteins. And we said that we can increase the temperature or we can increase the concentration, but there are drawbacks to it. So for temperature, when I'm increasing the temperature, I have more kinetic energy. That means I have more vibrational energy, more collisions, right? So more molecules are going to surpass activation energy. The temperature at which the enzymes work best is your optimum temperature, right? But you need to know that it's not a fixed number, it's a range. So the enzyme, the optimum temperature, is going to fluctuate around the normal range, okay? And like we mentioned, if we increase it, the drawback is it's going to lead to denaturization. For reactants, the reactant concentrations are low. That's why we're not going for these two methods. We use an enzyme, okay? It's a very easy question. You all can give it together, I guess. What's the answer?
C.
Okay, yes, it's C. So one thing, everyone knows why it's C? So basically enzymes are going to obey the thermodynamic law of equilibrium, okay? Which means that I'm going to, that there's a forward reaction, there's a backward reaction, right? Right? Yeah. So the enzyme is going to increase the temperature by equal amounts on both sides. So I'm not going to make the products more favored or the reactants more favored, okay? That's why we say they're going to increase the rate of forward and backward equally. Do not get confused with this. So, what kind of reactions do enzymes catalyze? Is it spontaneous or non-spontaneous? Spontaneous. If I say spontaneous, my delta G is?
Negative.
Negative. And it's basically thermodynamically favorable. Exactly. And so in simple words, I'm basically just saying that I don't need an enzyme for the reaction to occur. I want it. not need and want, two different things, okay? And revision from your energy chapter, if my delta G is positive, the reaction is non-spontaneous. And if it's equal to 0? Equilibrium. Can you give me an example of a reaction that has delta G as 0? Isomerization reactions. Perfect. Do you guys want me to choose, or like you guys want to give it together the answer? Do you want me to choose randomly? Is that okay?
It's C.
Okay, yeah, it's C. So the important concept over here is that there's a difference between activation energy and the individual energy, okay? So I'll give you like an analogy. Let's say I'm like taking part in a marathon, okay? And this is the starting line, this is the finishing line, okay? This is my pathway, a curved pathway, and my coach acts as an enzyme, okay? And he tells me to choose the straight path to the finish line. Mind you, I'm still the same person. If I had 100 kilojoules to complete the curved path, I still have the same energy to reach the finish line from the straight path, right? So my individual energy, which is here, it's not going to change. I'm just decreasing the activation energy, which is my threshold energy. Make sense? Okay. So, what determines the rate of a chemical reaction? I need enough energy to overcome an activation barrier, yes. Which is also, in other words, you can say what state? Transition state, exactly. So basically, that's what it says. Okay. In this diagram, it's basically like representing the energy of the molecules, okay? So when I say energy, I'm referring to kinetic energy, right? So if you look in the diagram, if my activation energy is high, there is a lower proportion of molecules that are have the lower proportion that are going to like take part in the reaction. They have the energy that they have, which is the kinetic energy, which is supposed to be equivalent to activation or more than that. So over here, only these proportions have it, okay? But if I lower the activation energy, there's a greater proportion of molecules that are going to take part, and so my reaction is going to be faster. Does it make sense? Okay. This diagram is extremely important. You need to be able to label them. I'll give you like 5 seconds to just look at it. Okay, so what's my pink line representing?
Non-catalyzed reaction.
Exactly. What about purple? Catalyzed. What does this line represent? Activation energy for my uncatalyzed. And this one? Catalyzed. What does this one represent?
Delta G.
Delta G, which is my Gibbs free. What's the formula for Gibbs free? Sorry?
Delta H minus T delta S?
No. My product energy, yes. Product energy minus my reactive energy. So if I do that, I get a negative answer, right?
Yeah.
That's basically saying it's negative spontaneous reaction, okay? So keep this in mind. It's a very important diagram, so have it, like, keep it in your head. This is basically the same diagram in your textbook. Now, for free energy of activation, you need to know the textbook definition, which is really important. In simple terms, we said it's the threshold energy, right? So in your textbook, it's saying that it's the amount of energy required to convert 1 mole of substrate from ground state, which is your reactant state, which is stable and low energy form, to the transition state, which is unstable and high energy, okay? I'll explain more, like I'll help you visualize where we're saying it's unstable and high energy in the upcoming slides, but that's the definition for it. We're good so far? Okay. So this is my transition state. Like we mentioned, stable and least stable and high energy that forms when a substrate is bound to an enzyme. When substrate binds to enzyme, it leads to formation of
Enzyme complex.
exactly. And then when it reaches the transition state, enzyme transition complex. Okay. Once I reach the transition state, the products are going to form inevitably. Okay. Yeah. And at the transition state, my bonds are partially formed and partially broken. So we say that the complex over here, it's going to have characteristics of my reactant and my product, both of them, okay? And like we already mentioned, only molecules that reach transition state will be converted into products. So this is going to help you visualize why we say it's unstable and high energy. First of all, what kind of reaction is happening? Dehydration? Dehydrogenation? Mm-hmm. Oxidation, exactly. I'll tell you why. Look at the functional groups, guys. This is the transition state. Skip that. What is this molecule?
Acid.
Acid?
Alcohol.
Alcohol, exactly. OHC. And then I'm going to be converting it into
Acetaldehyde.
aldehyde. Yeah. Okay, so this is an oxidation reaction. It's a revision from your chapter 1, I guess. Right? So over here, in the alcohol, these two H are going to leave, okay, to form the double bond. This one is going to leave as a negative hydronium ion, and this one is going to leave as a proton, which is positive, okay? So in the transition state, these two haven't left yet, okay? They're still bound to it, they're partially broken and they're partially charged. Now, since they're oppositely charged, there's going to be a force of attraction, okay? Now, since they're attracted, they're going to like strain on the they're going to have like a strain on the structure, which is going to make it kind of unstable. Make sense? And because by nature it's going to be straight, okay? By nature the bonds are straight. This structure is going to like counteract the instability, and it's going to use large amounts of energy to keep it like straight. So it leaves as straight, and then later can form together, like bond together and leave as 2H. Kind of makes sense? Can you guys like visualize why we're saying it's high energy and unstable? Yeah? Okay, so for transition state, we already mentioned they must pass over the transition state. But important key point is that the enzymes are going to bind more strongly to your enzyme transition state complex than your enzyme substrate. Okay? So it's really important. Keep this point in your mind. And this diagram we already explained, this formula, which is also really important. Okay, so this diagram, for sure you're getting a question on this. Okay, if it's a transition state, for sure you get a question on this one. It's so simple. It's basically just saying that an energy profile, if I have two transition states, which is here and here, right? So over here, each transition state, I'm gonna have their own activation energy, okay? First of all, you need to be able to label it. So let's just divide it into two. I have my reactant here, my product over here. The activation energy goes from my reactant to the peak. This is the reactant, it's going to the peak, okay? That's how you're labeling the activation energy. And then when I come to the transition state 2, this is my reactant, this is my product. From the reactant to the peak, yeah? Okay, another thing you need to keep in mind is that when there are two transition states, you have an intermediate formation. This intermediate is going to be less stable than your reactant and more stable than your transition state. Okay? And what is my rate limiting step?
First one. The first one.
The first one, exactly. So it basically means the slowest step of the reaction. This one requires more energy compared to this, right? So I'm going to take more time to overcome this hill as compared to this hill. That's why I'm saying this is my rate limiting step. Okay? That's all you need to know in this diagram. Make sense? So far so good?
Yes.
Okay. Can I choose? Okay, guys, raise your hands if you know the answer. Okay.
This is A.
Yes, it's A. So the key point from here is that... Oh. Was this already there?
Yeah.
Oh. Okay, sorry. The key point over here is that not all reactions or collisions are going to lead to formation of a product, okay? So yeah, they need to be in the correct orientation, and they need to have enough energy, which is equivalent to your activation energy or more than that. Okay, So if you talk about pH, first of all, the active site is lined by,
Amino acid.
huh? Yes, amino acids. Yes, amino acids. So do you guys remember the structure of amino acids from your proteins chapter? Do you remember the structure? We have an NH2 group, we have C, then we have COOH group, H and R group, exactly. So when I have more protons, my NH2 becomes NH3 plus. Exactly. So my charge is +1, right? And if I have less protons, my NH3 plus is NH2, as it was from before. My COO, it becomes COH, it becomes CO minus, right? It's gonna become negatively charged. So you don't only need complementary structure, you need complementary charge also for the reaction to occur. The enzyme to bind to the substrate, okay? These two are important things. So if I mess up with the pH, I'm messing up with the amino acid's ionization state, which is going to affect my catalytic activity. Apart from that, you also need to know that there is denaturization. So just imagine like if I have more acid, there's going to be erosion. So like if I have acid on my skin is gonna like eat away, right? So just keep it in your head like that. And if I have too much like alkaline, my environment is too alkaline, it's gonna become like more solubilized and like slimy kind of. Just keep it in your head like that. And just like how we had optimum temperature, we have an optimum pH. And in our body, we have buffers that are going to maintain the pH. Okay? These are examples you need to remember. Where is pepsin found? In the stomach. Why? Because we have which acid? Hydrochloric. Exactly. And so my pH is going to be? Low. But it's, 2 basically. And where is chymotrypsin found? Small intestine. And so my pH is 8, alkaline. Exactly. And what is converting my acidic pH to my alkaline pH? Pancreas, yes. In the pancreatic juice, you have a buffer, sodium bicarbonate, which is going to be released in the duodenum and convert the acidic into alkaline. So keep these examples in your head. Raise your hands if you know the answer. Okay, go ahead. Yes.
Active site?
Yes, exactly, active site. Do we all know why it's active site? Yes?
Binds the substrate.
Binds the substrate is the description. So you need to keep the description in your, like the key terms, keep it in your head. Here we have the key terms, unique 3D structure. It is lined by several amino acids. Weak non-covalent reversible interactions. What are they? We have 3. Ionic. Hydrogen bonds. And hydrophobic. Van der Waals are for dipoles. Okay? And over here we have ions, positive and negative charge. We don't have the dipole, the sigma plus and positive symbol. We don't have that. Now you have 2 models, lock and key and induced fit. From the name itself, you know it. Lock and key, it's rigid structure, okay? It's permanent, it's not gonna change. So we have a rigid structure, the shape and charge is complementary, and so the enzyme is going to bind to only one substrate, okay? But when you come to induced fit, induced basically means causing something to happen, okay? So in this model, we recognize that proteins are flexible. So let's say this is my enzyme, this is my substrate. When it binds to it, there is going to be like a conformational change that's going to get triggered or induced. That's going to kind of like move closer and make it fit better, okay? That's basically my induced fit. And so that way it's going to bind to more than one substrate rather than just one. Yeah? Easy questions, guys. No one else? Okay. Yes? Yes, you? Yes?
B.
Which one?
B.
B? Yes, exactly. Do we all know why?
Yeah, it wraps around.
Yeah, it wraps around. There is a change happening, see?
So how would the other one be?
The other one, it's not going to change. It's like rigid. Over here, like you see how it's open, and then when you come here, it's closing on the substrate. Just like I'll bind to it, and then I'm gonna close on it. That's my induce. If it's like lock and key, it's gonna just like be rigid. It's not gonna move. Yeah, no change. Exactly. So do all enzymes function independently? No. There are some enzymes that require non-protein components. These are cofactors and coenzymes. Exactly. So from the name itself, cofactors sounds inorganic, right? And then coenzymes, organic. Okay, you guys can keep that in your minds?
Yeah.
Okay. You need to know the examples for it. Cofactors, you have metal ions, alkali and alkaline. These are loosely bound, they play structural roles. For transition, you have tightly bound, they play catalytic roles, and then these are basically the functions of transition metals when they bind to the enzymes, what's basically going to allow the enzyme to do. And then for coenzymes, since they're organic, they're derived from vitamins, they act as carriers of electrons, atoms, or functional groups during reactions. What is a very well-known example of coenzymes?
Non-reduction further.
Yes, exactly. And these get chemically altered. So we know that NAD plus becomes NADH. It's changing, right? It's not the same. So we have co-substrates and we have prosthetic groups. Co-substrates are loosely bound. They're going to be regenerated by a different enzyme. For prosthetic, it's tightly bound. It's going to be regenerated in the same catalytic cycle, which is the same enzyme. Okay?
I have a question.
Yes.
Why don't coenzymes cofactors?
Coenzymes are not cofactors. They're two different things. Like there's cofactors and there are coenzymes. They're two different groups. Cofactors are inorganic, coenzymes are organic. Those two are non-protein components. Yeah? Okay. So for enzymes that require non-protein components, they are going to be present in two forms. Apoenzyme and holoenzyme. Apo, A, absent. So my non-protein is absent and so my enzyme is inactive, okay? For holo, it's non-protein plus protein. So like HH has active. Yeah?
Yeah.
Read this question really carefully. It's a tricky one.
Answer.
Don't say out loud, they'll choose it. Raise your hands.
I think it's C because you said that it's prosthetic.
Okay. Any other answers? B. Okay. What? D? Okay, how many of you say it's A? You say it's A? Okay, how many of you say it's B? Okay, how many of you say it's C? Okay, how many of you say it's D? Okay, the answer is B. First of all, it's already voted. Never mind. Okay, the answer is B. I'll tell you why. See, over here they're trying to like put a story, okay? They're trying to confuse you. Read the last part. They said they're non-protein prosthetic groups, okay? Yes, we all know that. But the question is, what is the protein part? Okay, that's your key term. My protein is only the enzyme. My cofactors and my coenzymes are the non-protein, okay? That's why it said, what's my protein part? Without my non-protein things, that's my apoenzyme. If it had both of them, that's my holo. If it only said what's the non-protein stuff, it's gonna be either of these. Yeah? So read the key terms really well.
Why is it not hollow and something?
It's not holo because over here it's only saying what's my protein part. If it said protein plus non-protein or like complete enzyme, then you choose holo. Okay? So this table is very important. No, it's so important. It's really easy to memorize it, which was done by our seniors. The method that they gave it to us, it's passed on from my seniors, and so all credit goes to them. I just like made slight bit changes on it, but it's a really, really easy way to memorize it, okay? And it's kind of fun also. It's gonna stick to you till the end. So I'll help you memorize the names first. Okay, so it's gonna get here. Okay, anyways. So you have B, 1, 2, 3, okay? Thiamine, reminds you of thighs. When you think of riboflavin, you think of ribs. When you think of niacin, you think of neck. 1, 2, 3. Thiamine, riboflavin, niacin. Yeah, we can keep it in your head. Now we're gonna halalify the skeleton. Put some clothes on. Okay. And okay. So 5, 6, 7. Put some pants on. Pantothenic acid. We're gonna give her a shirt, pyramid shaped inverted shirt, paradoxine. Okay. Then we're gonna give her a bow, or you guys can remember as brain rot meme or whatever you like. So just give her the bow. Okay. So 5, 6, 7. Pantothenic acid, paradoxine, and give her a bow. Okay. Then give her some boots. Vitamin B12. She's a girl. She deserves flowers. Folic acid, flower. And then give her a cape, vitamin C. Yeah? You can keep it in mind. 5, 6, 7. Pantothenic acid, paradoxine, bow. Biotin. You have a doubt?
No.
Oh, okay. Biotin. Okay. And then give her some boots, vitamin B12. Give her a flower because she's a girl. Folic acid. And then vitamin C. Give her a cape. Yeah? So it's an easy way to memorize it. It was passed on from our seniors, so all credits to them. So, okay, obviously you need to memorize this table somehow. Just like try to make connections between them. Something very important is know what the vitamins are and know what the coenzyme forms are. Okay, because usually in the exam you're going to get like the function, and then they're going to be like, what's the vitamin doing that function? Okay, and then they're going to put both of these. They're going to put the vitamin and they're going to put the coenzyme. So do not get confused. Know what the vitamin is, know what the coenzyme is. Okay? So one way to keep it in mind is like thiamine, T transfer, then you have riboflavin, and then nicotinic acid, and N, F, like it's a way to keep it in mind. And then paradoxine, paradoxyl, amine, amino. Then you have like pantothenic acid, A, acyl. And then for biotin, you can like keep it in your head like ABC, right? So B, and then C, carboxylation. And then for folic acid, in the coenzyme form, you have it in the end, folic acid. F first, like one carbon group transfer. Then for vitamin, another name for vitamin B12 is cobalamine. Okay, so in both examples, in the end, you have cobalamine. Okay, so vitamin IN, intramolecular rearrangements. Okay, and then ascorbic acid hydroxylation. I think you took it in one of the chapters, this hydroxylation part, where it's also mentioned. Now you have the naming systems. Easy. Why do we need naming systems? Why do we need anatomy? Why do we have these anatomical terms? To make it easier, or like to eliminate confusion, right? So we all are talking about the same stuff, right? Same thing applies over here. We have two naming systems, that's systemic and recommended, okay? Systemic is used by like biochemists, and recommended is what we use, okay? So you have eliminate confusion and standardized enzyme names. Classification is based on chemical reaction catalyzed. There are 2 parts to it, 4-number classification and 2-part systemic name. You need to memorize this example for your exams, which is easy. It's 4-number classification, it's like EC111. That's your 4-number classification, okay? And then you have 2-part systemic name. That's your alcohol, NAD plus oxidoreductase. That's your systemic name, 2-part, okay? And recommended is basically the names that we use in general. That's like your alcohol dehydrogenase. That's your recommended name. Yeah?
Is there any other example with the numbers other than this one?
No, I think this is the only one that was in the textbook and what we also studied. So this is the only example you need to know. But if your professors mention others, which I don't think so there's any. This is one. So now you need to know the 6 major types of enzymes. Again, very easy because it's in the name itself. Okay? So you have oxidoreductase, oxidation, reduction, redox reactions. It's going to catalyze redox reactions. Transferase, transfer functional groups between molecules. Hydrolase, which is water. Hydro means water, right?
Hydrolysis.
Hydrolysis, yeah, basically. And then lase means breakdown. So I'm gonna mostly break down the CO, CN, and OP bonds, okay? And then for lyase, It's also breakdown, but without water. But the main key term over here is double bond formation or elimination of double bonds. So either side, I'm going to have a double bond. Okay? And then isomers, intramolecular rearrangements, and then ligase, think of it like the G, which is glue, kind of. Okay? So I'm gluing two substrates together to form a bond, molecule. So this reaction usually requires ATP. And you need to know them in order. So this is just a mnemonic, only transfer high-level ideas logically. Okay? Now for oxygen reductase, you have the coenzymes that are going to be present, which is NAD plus and NADH, FAD and FADH2. You need to know the example, such as dehydrogenase. It's simple. Dehydrogenase removal of hydrogen, reductase, reduction, and then like oxidation, oxygenases, oxidases, and peroxidases. So it's kind of easy to keep it in mind. And here you just look at the reaction. It's like NAD is becoming reduced, and then my alcohol is oxidizing. Yeah. So it's easy, like you can identify it easily. Do you guys know this mnemonic or oil rig?
Yes. Yes.
Yeah. So oxidation is loss of electrons and hydrogen.
Yes.
Yeah. And reduction is gain of electrons and hydrogen. Okay, it's a very famous mnemonic. So for transferase, this is a very important enzyme that you're also going to learn in biochemistry too, which is this is the first step of your glycolysis, but you don't need to know that right now. All you need to know is that hexokinase or kinases usually require the cofactor Mg2+. Okay? And then it's transferase, so it's ATP over here. ATP has 3 phosphate, right? So I'm basically transferring 1 phosphate from here to here, as you can see. Okay? And then my ATP becomes ADP. Yeah?
What happens to the hydrogen atom?
Hydrogen, it leaves as H plus ion. Yeah, it leaves as H plus ion. And now you have your examples. Amino, carboxyl, carbonyl, methyl, phosphoryl, and then from the name itself is trans, so the name of the enzyme it usually starts with trans, so trans carboxylases, trans methylases, trans aminases. Okay? And then hydrolase, as we said, we need water as a reactant. An example is chymotrypsin. This is basically like breakdown of peptide bonds, which is going to lead to formation of amino acids, exactly. And then esterases is an example, phosphatases, proteases. Esterification, do you guys remember the reaction for esterification?
Yeah.
Yeah? It's carboxylic acid plus alcohol. Under like what environment? Acidic or alkaline? Acidic environment. It's going to lead to formation of ester plus water. And it's a reversible reaction. Okay, keep that in mind. And then you have your lyase. Like we said, double bond is your, like, what do you say? Key to identify if it's lyase or not. So over here, usually when I am breaking a bond, there's going to be formation of like H2O, COO2, and NH3. Okay, they have like double bond. So when I'm breaking this has double bond. It's formation of double bond, right? Make sense? Okay, so that's your lyase reaction. Know the examples really well.
Doesn't lyase break down the bonds?
It can break down or form. So it's either like there's going to be double bond and either like a reactant and there's atoms adding to it, or it's going to be the other way around, just like this. Addition or removal. Okay? Isomers, same atom number on both sides. We all know that, right? Again, you need to know the examples. And then for racemase, epimerase, and mutases, I think you're going to take that in carbohydrates, so you know the example. And yeah, it's the same number of atoms on this side. If my C is 3 over here, my C is going to be 3 over here. It's the same number of atoms on both sides, okay? Yeah. And then for ligase, like I said, glue, okay? So I need ATP for this to happen. Examples, also, 1 second. One thing you need to keep in mind, this is synthase. For lyase, you have synthase, okay? For ligase, you have synthetase. Do not get confused between the spellings, because they're going to confuse you. Over here I have ATP, but ATP is going under hydrolysis to form ADP plus PI. My PI is not joining. If it was joining, it's transfers. Okay? But here it's not joining, it's just releasing the energy. Okay? Okay, I'm gonna ask you guys to do the technical questions. Do we have time? Can we do it really fast, these ones? First one, yes?
Transfers.
Exactly, transfers. I have highlighted why, so since we're running on time, I'll just like go fast. And then, yeah, it's lies. Like it's, okay.
Oxidatives.
Isomers. Hydrolyse, perfect. Your key, like, formation of like carbon dioxide, that's your key point. Yeah. Okay.
What is the carbon dioxide with double bonds?
Double bond carbon dioxide?
Yeah, what is that? What does carbon dioxide have to do with double bonds?
Like it's needed for formation of a double bond basically. So in the reactant side you have double bond forming. Does it make sense?
Sorry.
Wait, I'll come to you to explain the lies because we're running on time. I'll come to you after the lecture, okay? This one? Yeah. B? Yes, exactly. Okay, so this is the reaction for esterification. Keep it in mind. No, it's acidic. No, the forward and backward. Okay? It's a very important reaction. Now, you have 4 catalytic mechanisms via which enzymes work or bind to the substrate. You have proximity and orientation. Basically, it's just saying that my substrate should be in the correct orientation and it should be close. That's all it's saying. For my electrostatic, it's saying like, you know how my active site, it has amino acids, so it has charges, right? So if I have water over there, it's kind of gonna dilute the charges, and so my strength is not gonna be that strong, okay? That's why we keep the active site anhydrous, no water over there. So that's all it's saying over here. And then for acid-base, like we already mentioned, amino acids could be acidic or basic, and then like if I increase the H plus or reduce the H plus, it's going to affect like the charges, which is going to affect my catalytic activity. You need to know these examples, okay? Memorize them and their side chains. And then, so far we've been saying that all the enzymes are going to bind to the substrate non-covalently, right? But then there are some enzymes that are going to use covalent binding, okay? So when they bind covalently, they're going to lead to a formation of an intermediate. Keep that in mind. There's going to be an intermediate formation which is reactive, and then later it's going to break down and form the product, okay? They both mean the same thing, but they have different definitions. Can you imagine?
Maybe a simple description of the chemical reaction process, illustrating our product.
Sorry. For mechanism, which one?
It's the second one.
Mechanism is second one? Are you sure?
Reaction mechanism, the second one.
Mechanism is second one.
Reaction mechanism.
Mechanism, yeah, exactly. Reaction mechanism is the second one, and then mechanism is the first one. They're basically the same thing, but if they give you this, your answer is this. If they give you just mechanism, your answer is this.
Yeah.
Okay?
Reaction.
Yes, exactly. So that's it from my part. Now I'm going to leave the floor to Farouk.
We're going to start enzyme kinetics. I know it is a little bit frustrating, hard a little bit, but inshallah, simple, step by step, you're going to understand it. Good? Now, in this lesson, you have 6 main bullet points or subjects, let's say. We are going to talk about an overview of the enzyme kinetics. We are going to explain Mikhail's Menten, line waiver, multi-substrate reaction, inhibition, and lastly, enzyme kinetics, metabolism, and macromolecular crowding. Oof. Long name. Now, enzyme kinetics. يلا. طبعا for me, you have to bear with me. I have going to pick. Hello? I'm going to pick person, and he have to say, if you don't know the answer, it's fine. We will stick and together. We will make you reach the answer. Enzyme kinetics. Any idea? What does this mean? What does enzyme kinetics mean? يلا شباب.
The rate of the velocity of the reaction.
Right, حلو. Now kinetics, as you said, it is the rate, speed, movement. Okay? So here, by definition in the book, it says it is the quantitative study of the enzyme catalysis. حلو? Simple terms, it tell you how fast. حلو? Focus on the word fast. How fast the enzyme work and what affect the speed. حلو? What does quantitative mean in this book? But simply, it is not just saying this enzyme is slow. No, this enzyme is fast. We have to say this enzyme is fast because we measure numbers, rate, and equation. This is what quantitative means. Good? Hello. Moving to the next point, we will have why. Oh, sorry. Yeah. Why do we study EK? Enzyme kinetics. I got a mnemonic. Try to get any idea. 4 letter. أيفر. يلا تفضل. يا جنتلمان يلا. أي شيء يلا. بداية الكتاب. It's in the start of the book. Why do we study it? Why do we study enzyme kinetics?
You know the speed, the rate.
حلو. يعني close.
Affinity.
حلو affinity we said affinity حلو affinity يلا A is for affinity تمام. So by studying enzyme kinetics we learn that we can learn how strong the binding of the substrate to the enzyme was. Good. Now second point I يلا I inhibition. Nice. Inhibition or inhibitors. By studying kinetics we know how enzyme, drug or a toxin can slow down or stop the enzyme from working. Good? Then third point, F. I show you something. Little bit high.
Frequency.
No, not frequency. F. هي بالكتاب in the book it's أصلاً يعني a little bit misleading. It says forces. Now we say forces يعني bunch صح ولا لا؟ But no, it is not. Forces they mean like the environment of the enzyme. حلو? We study kinetics and measure this enzyme is working in what environment, the best ideal condition that it works in. حلو? So there are different conditions in the environment the enzyme can work in. Let's say this enzyme likes to work in a condition where the pH is low. Hello, you took with Laiba now, chemo, the one in the stomach. Hello. So this is what meant by forces. It is just like by studying enzyme kinetics, we know the optimum condition the enzyme, the specific enzyme can work in. Hello. Now last point is R, which is regulation. يعني we know enzymes are in the body and they do specific reaction that are metabolic that way. يعني you eat something, يعني break down this something, this is all by enzyme. So by knowing the kinetics, we learn how they do this. Good? Now we move to the second point, which is rate and reaction and initial velocity. يلا أعطيك some this video. Rate and reaction. يعني شنو معنى rate and reaction? What does rate and reaction mean?
Basically, they're saying for every reaction, there's a specific amount of time that the reaction takes place in. So the rate, how often it happens, and the time for the reaction, and
time, product,
and the product
substrate,
and the reactants.
Good, exactly. So now rate and reaction. Reaction, simply, substrate A, go to product B. Hello? Now for rate, which is velocity, it is the speed. It is the same thing. This, يعني our friend in high school, velocity. We know it, يعني equation and mathematics. It is the same thing here. So you have this equation. You don't need to memorize it. Hello? I will tell you which equation you need to memorize. This one, just understand it. Now we have A, which is the substrate, and we have B. rate, which is velocity, it is the concentration. How much of a substance is there at a time? How much of a substance how much of a substance is changing over a time, over a period of time? We have here minus A, which is the concentration of the A that is changing over a period of time. It is the same as B, because substrate goes to product. صح? Am I right? Am I right or not?
Yes.
Hello. Now, what does this minus mean? Why?
Decrease.
Hello. Substrate concentration, it is decreasing. Good. Now, initial velocity. We can't, in kinetics, we can't measure the velocity from this equation. We have to measure this, I call him the cute guy. Hello? So the velocity, initial velocity, it is the same. The velocity right at the beginning of the reaction. So why? Why do we do it? And why do we measure
To
him?
measure the rate of the velocity without the enzyme.
Hello.
Because
Yeah,
the
close.
substrate is mostly in the beginning.
Hello. Yeah,
The
exactly.
reverse reaction still did not occur.
The substrate, it is still bigger. We have more substrate. The whole point of this, why do we take him and measure him? Because you have the reaction, right? This reaction in the body, it is not just one way, it is two ways. We have substrate and it is moving to the product, right? When it finishes, sometimes it go back. We don't want to measure the going back to the substrate. We only want to measure the first one, which is to the product formation. Therefore, we want the initial velocity. This will tell us the rate that the substrate is changing to the product. And خلاص, that's it. Now, as we said, here it is no backward reaction. تمام? We said, I bet you, this mnemonic, he's a chill guy. Things are still chill, simple. There is no mixing. It is still just the substrate. It is present. And also, this is, you imagine yourself, hello, and you see, you didn't study at the beginning, and the quiz came, and you see, mashallah, you have this much of material. What you do in this situation? You'll panic. You will be fast, right? You will work at the maximum velocity. Same thing here. In the beginning of the reaction, the enzyme have a lot of substrate. Therefore, he is working at its maximum capacity. Hello? So, this point we want to measure it. Last here, we finished it. We move to rate of reaction. It is the same thing, but just with the equation. We said this one, we can't measure it, so we change it to this one. What's the difference here?
It's only the product. The
So
substrate.
the substrate.
Later on, just a simple thing. What's the difference between this and this? We have VO and we have substrate. What is the change? K and X, I knew. We don't know it, right? So this one is letting us to measure it. First, let's start with K. K, it is the rate constant. You remember when we say forces, right? For 2 slides, it's the environment. Each enzyme is working different at different condition. We have to measure this. We have to put this in concentration, right? ولا لا? So we have this rate constant. This is just a factor that depends on the reaction rate. Hello? For the X, it is the order of reaction. هذا we will talk. We have a nice conversation in the next slide. Good. Then we begin شوية حبة molecularity. شنو molecularity? Any idea? Present. Here.
How many molecules reacting? What types of substances are there? How many types?
Good, exactly. So molecularity, it is a theoretical idea, basic knowledge. You have what? You have unimolecular reaction, which is just one molecule going to be a product, right? Bimolecular, it is two substrate going to a product. This one you don't know, it is just a picture. So it is tri and quadra and it finished. So this is a theoretical idea. If we have unimolecular, it is one molecule and one substrate going to a product. Bi, it is two. Hello? This one, it is the same thing of the order of reaction, but a theoretical. Order of reaction, they take this into an experimental view. Hello? So it is the same thing. It is just how many substrates are working. Is it one? Is it two? Is it more? In this, we want to, it is different because the more substrate you add, the more faster the reaction. The same example I just gave you, one with the heavy material and he started to work faster. This is the same thing. And now, just let me do this. This is the same equation I just presented, right? Right or no? Hello. We have, this is the order, right? Let me change it a little bit for you. This rate equals K, A, B, M, N. You don't need to memorize, just understand. M and N, if we combine them, this is the total number of the reaction order. Hello? So let's say if you have, this is substrate 1, and it is only just one molecule, so we put order 1. We put another one for B. B doesn't have to be another substrate, even if it is the same substrate, but we have 2. So it is now 2. 1 plus 1 is 2. Hello? Or 1 plus 2 is 3. This is the order of reaction. Hello? So it is, we have amplified the idea of multiple substrate working in the enzyme. Good? Hello. Well, I feel you didn't understand it.
No, I understood.
Can you summarize?
Oh, and you said that the M or N, if you add them together, you get the order of the reaction. Let's say you have N is 1 and M is 1, you add together, you get the second order reaction.
Hello, it is the same thing. This is just to give you an idea. Come on. So, as you say, it is just like an adding process, right? Mathematics, simple mathematics. We have 0 first and second order, depending on how much. Now, why? What we will get from knowing the order?
The graph or the break.
Mm-hmm.
So for example, if it's like first order, then it's a linear graph that goes upwards.
Exactly. So order, we said now, the more substrate you add, the faster the reaction. Hello, Allah. By faster, imagine this is an environment and this is an enzyme. Hello, you have the active site, صح ولا لا? Right? Now for the substrate to come into in the active site and bind, it have to walk. The more we add substrate, imagine this one as a substrate and this one is another substrate. They are always moving. So he push him. He's faster now. So he's faster to the binding site. This is what it means by order. The more substrate you put, the more they are moving faster. The faster the period, or the shorter the period they have that it has to be for them to bind to the enzyme. Hello, good. Now for order, we can classify it as 4 things: 0 first to second, or something pseudo. Pseudo, it means liar, chadab. Hello. 0, it says what? It says that the speed, it does not have to do anything with how much concentration you put. Some enzymes work in this condition. Tamam? You add substrate, خلاص, it has like a specific condition, stability. Now for the first order, it is just 1. So this one is like the general idea. It is the same thing as this: more substrate, more product, faster product, faster formation. Hello. Second, it is double. Good. Pseudo is just a special condition. This is an enzyme and it is one substance. Hello, wala la? The other substance is H2O, water molecules. Now water, we have, mashallah, 75% of you is water. So you have a lot of water, صح ولا لا? Tamam. If it is a lot of water, what does this mean? The water says to the enzyme, خلاص, go play somewhere else. I won't deal with you. I won't try to compute with you or do something with you. Therefore, we put the water or the pseudo, we classify it as a first. You got the idea? You didn't get the idea. 2 things, حلو ولا لا? Water and the enzyme. should be what? Should be second. صح ولا لا? Should be second.
Pseudo.
Water is too much. It don't want to play this game. It say خلاص, you are the only one. It is only the enzyme. First order. Good? خلاص. Moving on, type of order. This one is an important. Hello? We just said it is 0. وهذا يعني I'll go to spam you with the table. You get scared now? You're not scared, huh? 0 order and first order, second order of pseudo. I want you to يعني, memorize these two. Yeah, these two. The rate, this one, the equation I just mentioned, the K1 rate, and then the pseudo, it turns into K1. And I want you to see this one. Now, we study kinetics, and then we say it is a quantitative, we have to put it into graphs and equation. On the graph, if we put this equation, it will give us this. Unfortunately, the order of the reaction, this is used in general chemistry. Hello? Why it is used in general chemistry? This is in kinetics. This is the order. Didn't we see the equation right now, the X? This is equation. Now for enzymes, if you add more substrate, it will keep working until it reaches a point where it says خلاص. All the enzymes, the active site, hello, let's say you have 20 enzyme. All the active site is bound, there is a substrate bound in the active site. So if you add more, خلاص يعني it won't, where it will bind? Nothing. So this is the maximum point. Therefore, the normal order can't work here. Hello, another solution will come just in the slides. But this is what happens, and after we write the equation, this is the equation after of the enzymes. So instead, in 0, it is the same. It is a flat, just a flat line. I just saw an خلاص, I will give it to you. For the first, it is hyperbolic. Second is sigmoidal, and pseudo, it is the same as first one, hyperbolic. You got it? I will show you the graph because you seem confused. This is sigmoidal, and this is what? Hyperbolic. Now this one is in which condition? First.
And also the last one, the pseudo.
Pseudo. Also
That's it.
0. You see this?
Oh.
It is a flat line in the end. But this is, who will tell you this about this? Mikhail. We will get to it. The second subject of this lesson. So I want you, what I want you to know that we have orders. We have 0, first, and second, and pseudo. Hello? Pseudo, same as first. 0, flat line, like this. Hello? First, hyperbolic. Second, sigmoidal. Allosteric, it is what allosteric? Allosteric, you see this enzyme? This is one substrate. This is, let's say, another substrate. So we have 2 active sites in the enzyme, 2 substances, second order. Therefore, it is sigmoidal. Good?
I have a question.
Yes.
For the 0 order, does that mean that regardless of the concentration, it just happens at its own pace? Like the reaction happens at its
It
own pace?
continues. You add more substrate, nothing changes. It is خلاص, maximum velocity.
Okay.
Nothing is changing. Flat line. You add more, it is not changing. You add more, it is not changing because all of the enzymes are occupied with the substrates. No more place left for the substrate to bind in. Good? This is hyperbolic, this is sigmoidal. Yalla. Question. You see the graph? This is A, B, C, D. D. Explain.
Hyperbolic first order.
Hello. بعد ما شنو?
Non-allosteric.
What is this? Hey.
Allosteric is the second order.
Simple enzyme معناتها it doesn't have phosphatic group, it's just amino acids.
Complication. So this is hyperbolic. We all agree on. صح? Now non-allosteric. You remember this right just before? This is 2. This is called allosteric enzyme because there is a space other than the active site. It is like a second active site. Hello? We call it allosteric allosteric site. Substance go and bind to this enzyme. This substance is called allosteric effector. Depending on what it will do, it can inhibit the enzyme and it can activate it. This we will talk in the 5th lesson, which is the regulation of the enzyme. But it is just this idea. You have another active site, substance bind to it, either inhibit it or activate it. Good? This one is what? Allosteric. It is sigmoidal. It shows this shape. And this one is hyperbolic. Hyperbolic, it is not allosteric enzyme, just normal enzyme. Good? Go.
Oh yeah, and all allosteric enzymes will have sigmoidal effect?
Yes. All allosteric enzyme, allosteric, sigmoidal, fast. Yeah, because it is two things. Some order of reaction. We continue on. The book mentioned these 2 slides. Hello? You just asked about the 0 order, right? This is what I mean. The hyperbolic in the enzyme condition, not in the normal general chemistry condition. In the enzyme condition, it says in the first part was the first. The more you put, the more speed you will get. Until it reaches a point where you add more, it is the same speed. This is 0. This is the graph for the enzyme. It shows both. First part is 0, second part is 0. Hello? This graph, it is just mainly telling you that this is the product formation and this is the time. Hello? We know the reaction is A to B. It is not خلاص A. There will be a time, the substrate started to decrease. Natural thing, you are going to move from this place to this place. So up until here, it was the product formation. It was going on until there are no more substrate here. So product formation finish. Logic thing, right? Wallah, you didn't understand it. You understood? Alhamdulillah. This is the little bit coloration, so you can see first and second. طبعا this is all of this is just the Mikhail-Menton, which is the second factor. This is it. It's basically solved the problem of the order. This is what the 2 scientists did. We will talk a bit about it so you can understand it and amplify the idea. Now we are going to move into something called half-life. Yalla. Ladies at the back, can you answer? Half-life.
Basically the time it takes for half the amount of the substrate to change.
Exactly. Mnemonic, Bachman, this is was presented by our seniors. This is substrate 1, 2, 3, 4. Bachman come here. It takes 3 seconds. This is half time. So it is half of the substrate, the time that was the time that it gets for the half of the substrate to be converted. This is half-life, basically. Yalla, now we begin with the Michael-Menton. Can anyone, we just said Michael-Menton what they did do. I call him Michael, he is Mikhail. But you can simplify the material you have. Hello? Yeah. Tell me. Eh? What was it? It's fine. Mikhail-Menton. Huh?
Talks about the affinity of the enzyme to the substrate.
Kind of.
The scientist who wants to measure the rate from first order to 0 order.
Close. Yeah.
Change of order, how
Close.
To measure the Km.
Still, we will get it. It is the same idea of the order, but they fix the problem that in order in general chemistry we can't use it because there is a maximum line for the enzymes. They say what? Or should they explain the same definition? The enzyme rate depends on the substrate concentration. They give this equation, E and S, it will turn to ES. This is an intermediate, ES complex, ES, good? And then what? ES, the enzyme, we say enzymes never get used in the reaction. They just convert the things, they don't. So here we have it left, خلاص برا out. And what we get? B order product, sorry. Good? حلو. What are these things? MashaAllah, these things are just the rate constant, the same equation. V initial equals K A X K. This is the case. Hello, for each of the reaction. Formation, and we say and there are chemicals, chemical reactions that it is going backward, right? So we have this is the K constant for it. And the second one is this one, the K2, the product formation. Good? Hello? Then K1 in this case, it is, and we can neglect it. Why? Because the enzymes mainly focus about turning the substrate into the product. So this one will be small. So we cancel it. We don't take it into consideration. Hello? Come on. Then now we are moving on from, they keep talking about multiple stuff. At the end, they say that this is the reaction, the equation we can use for the enzymes. This is the same V initial, the same thing. You can take it. K, the same constant. Now we take ES instead of S or A, substrate, right? Basically, here they took the second part of the equation. Let me get back. They took the second part of the equation. Why? Because we want to focus on this. We want to measure the kinetics for the product formation. صح ولا لا? So we take the second part of the equation. Who is the substrate in the second part of the equation? This one. So we take it and put it instead of the A. Good? Now this one, as I told you, it is an intermediate. So it is always changing, either going back or forward. So we can't really take it into the equation itself. We have to put what? We have to put the enzyme and the substrate, the things that we can calculate in a concentration. You have a jar, you have an enzyme in it, you can put some, mashallah, special equipment, and you can count the concentration of the things. صح? You can't count, wallah, this molecule, it is just enzyme and substrate bound. It is always moving, bound and then go, bound and then khalas go, and then the other things, enzyme and product. صح ولا لا? So we want to measure the things that are separate, the free enzyme or the total number of the enzymes and the substrate. Good? Then moving on, this is what I want you to memorize. This one equation. They changed this and they put the E and S, and then they changed a lot of process and equation. Last thing they ended up with is this equation. Hello? This is called the Michaelis-Menten equation. We will, I have a slide that explains each part of the equation, and you have to know what each part of it means. The second thing they took, that they made the Michaelis-Menten model, or just the graph. Hello? This is the same graph we used 2 slides ago. This is the slide, right? That was before this we said the hyperbolic. It is the same one. And instead the reaction we said order, we can use it in general chemistry. صح ولا لا? Hello? So they changed it into this one. This one I want you to memorize. We said this one is what? This one is what? Hello. This one is what? Sigma. Then this is the first part. We say what? Sorry. The first part is what? First order. More substrate you add, the more reaction rate it increase until it will get to the part where khalas, every enzyme is occupied. The more you add, nothing will happen. It's the same thing. It's a flat line. Moving on, we have now this is I explained. You have this one. You have to really know what each part. This one is the substrate concentration. Easy, the same thing. S. This one is what? This one is the velocity. The same thing, the thing that we want to measure actually. Vmax, it is the final velocity it can reach. The rate when all the enzyme active sites are saturated. Saturated means occupied by the substrate. Good? Now this one. يعني شوف I put acute limit يعني the attention span should come back صح ولا لا؟ This is what? This is Km. This is Michael's constant. تمام؟ This one, you see this one, يعني ما شاء الله it's evil looking. This one basically tells you what? It tells you that the more of it, the less the affinity will be. This one, it just measure for you or something to tell you about the affinity of the enzyme and the substrate. Good? Hello? The more you have it, the less the affinity, the less the love between the enzyme and the substrate. Hello? So it is a bad guy. We can remember it this one. We have يعني a specific point in the graph that we خلاص. This is Km. You see this? This is what? Vmax. Half of it, the number on the graph on the substrate concentration, this is it. So Km or Michael constant, it is the substrate concentration when the Vmax is half. Hello? This one you have to remember.
When the Vmax is half, is that half-life as well?
No. Half-life, it is just half of the thing. Half of the substrate, this is the time you want to measure. This one is the substrate. Hello?
What's the significance of it?
What? Hello.
Km.
The Km, it basically tells you about the affinity. We just said the more you have it, the less the affinity, the less the enzymes and the substrate يعني can come faster together or يعني interact together. Good?
يخرب العلاقة.
ها؟
إذا كان موجود يخرب العلاقة، إذا ما كان
أي بالضبط. يعني if he is present and he is at high concentration, it will what? It will يعني disrupt the reaction or يعني it will decrease the affinity. And you can see here يعني decrease the affinity. It means what? It means it will get يعني more time for the substrate and the enzymes to get back.
Is it because it's indirectly?
And exactly, it is because it is in the down. So the more, the less velocity. You get it? Hello. Now we have something called steady state assumption. It is the same thing. You have this ES, right? Hello. This is an intermediate. Basically, it says what? It says that this direction will have the same يعني quantity or the same thing as this. The rate of the ES formation, it is the same one of the ES breakdown. Hello? From this we will get to the equations. You have this one. I just explained that we take this part, implement it in this. This is the first one. This is basically يعني you open the book and you see multiple equation. It is just explaining this process. It is just taking this part and خلاص we want to turn this in the product part, and we have to put some things that we can calculate, the substrate concentration and the enzyme concentration. Good? So now we put the ES. We have a problem. ES is always changing, so we can't put it. We want to put the things that we can calculate. ES and S. E and S. Sorry. Hello? طبعا this it will turn to what? This one it will turn to the same thing. This is I want you to memorize, and we know every part of it. This one is what? Velocity. This one Vmax. This one
The amount of substrate.
this one
The half the time. Half of Vmax.
Michael's constant.
حلو لا اي ما sorry Michael Kors. Then what's the point of it? Why do we have it?
Half of the Vmax.
حلو بس خلاص. The what? Half of a Vmax of what?
The substrate.
The substrate. It is the substrate concentration at half of the Vmax, basically. What it does, it tell you about the affinity of the enzyme. The more you have of it, the less the affinity, the less the velocity. Hello? على العكس, the opposite thing, the less the Km, high velocity, high affinity, high velocity. Good? Hello. This is the process of it. This is all the equation in the book and more. آخر شيء, the last thing, they get this one and then this one. Neglect this. don't حتى يعني it is just a process. Only focus on these two. Km, it is the one that we said. It is these two, the right, this one. These. Hello? From these we can calculate the Km. Good? Now basically you are going to get confused. I have to put 1 over ولا -1 تحت. This one is going in what direction?
Forward.
Forward. And this one is going what?
Forward.
Forward. حتى. This one is going what?
Backward.
Backward. If we want to take these, we have to put the first backward, the second forward. وجواها the first one. Hard, right? Dissociation over association. Basically, you have the ES, right? The one that move you to the ES, this is called the association. Down. The one that move you from ES, خلاص, ES is braked. This is the D association. It is 2. Because this one, it will get you back this, and this one is will get you back. So this one is lost. Dissociation over association. K1, K minus 1. K2 over K1. K minus 1 plus K2 over K1. Good? We will move on to something called Kcat. Kcat is basically,
yeah. Understand the equation. شو نعمل K equals Km minus 1.
This one, the 1 and the 2 and Hana. This one is the equation that we use for the Km. It is basically these guys. We have ES in the middle. صح ولا لا? The one that association over dissociation. These ones, the one that gets you to the ES, we put it down. It is only one. It is only this one. Hello? Put it down. The one that ES break, it is the seconds. These the -1 get you from this, so it is not formed, and this one it is braked. So we put it up. Now Kcat, it is the opposite. I put an image here. Cute, pure, hello. It basically what it is. It tell you the number of the substrate that is converted to the product per enzyme molecule per second. So this one is just telling you how much substrate you are converting to a product per second. So it's a good thing. The more you have it, the better the enzyme is working. Right? Right or not? Hello. This one, they combine both. The good one and the bad one. The less this, the more that, the better the enzyme. This is called catalytic efficiency or specificity constant. Hello, you have to remember this. Specificity constant combines the speed, the more speed, the Kcat tell you about and the more of it, the more speed you have. Km, the lower you have, the more affinity, the higher the velocity. They combine it both, and what it will give you, it will just tell you that this enzyme is working good. Hello, the more you have catalytic or specificity constant, the better the enzyme is working. Good?
Yes.
Feel you are not. Hello? There. يعني there is also a limit, the final point. يعني okay, the more you have this thing, the more better it is, but it will get to something. يعني خلاص, it is the final thing. What is this? This is the environment. And we have the matrix, hello? And this is the substrate particles. And this one is the enzyme. Even if you have a lot of substrate, a lot of things, there will be something kind of friction or something kind of the environment, hello? The environment of it, this is a concentration you have. This is the upper limit because the diffusion up to this limit, it was increasing. And then خلاص, this is the maximum thing the substrate can move in the environment or in the matrix. Good? We didn't understand. Tell me, why? What's happening?
What do you mean by the environment?
Environment. Okay, what I mean by environment, خلاص, the space that this thing is occurring. The space, enzyme here, substrate here, the around thing, it is not moving in the air, It is moving in like, let's say, the cytoplasm. Hello? The cytoplasm is a liquid, let's say, so will be kind of a friction. This is they call it, this is the maximum thing that the substrate, the fastest that they can move through. Hello? Just know that this one is a good guy. The more of it, the faster the reaction. Up until there is a certain limit, this is the limit. Okay? Now the enzyme with the maximum catalytic efficiency, we call it catalytic perfection. Good? We move on. Now for units, you have 3 units. You have international unit, specific activity, and catalyst. It's just like something that the unit of the velocity changing. Hello? International unit is 1 micromole of substrate per minute. This one is the same IU but per milligram of protein. And this one is titled something new. Hello, they newly added this. Now, you remember the graph? We used this one, it's a little bit curved. Laiba, he was a guy, he said, I don't like something twisted or curved. I like straight things. Hello? He don't like, ما يحب اللف والدوران. He likes straight things. So he converted the graph into a straight line. How? You remember the equation we used? Wait. This one, the equation, I just told you to memorize and to know. Basically, he played with it, changed stuff in it until what? Until he got this. This one is the second thing you have to memorize. This one is the equation of the Laiba-Burke plots. Good? Now why? Why did he change it into a straight line? Here you can't exactly determine the number of the speed or the number of the km or the number of the substrate. In a straight line, خلاص you can. This is a dot. This is a specific number. So we use it to what? We use it to determine V max and Km because these are mainly the things that we want to, we focus on precisely. Hello? Good? Any question? I feel you are not understanding. Good? Yalla, we move on. Now, for this equation, we are going to take it part by part. For a line equation in mathematics, we use this equation. Y equals mx plus b. Simple. This one, it is the same as this. Every part, it takes like one part of this main equation. So in the end, it will be a straight line. Y, it is a changeable factor. Hello, this is the result you will get. It is the what? It is the reciprocal of the velocity. Here, we don't take to change it into this linear equation, we have to flip the equation. So everything in the equation, it was above, now we move it down. This is a very important point. You have to know that in Laiba-Burke plots, the equation is flipped. So when you see a graph, you will flip the answer. Hello? The closer this point is the highest thing because of this. Good? So we want, let's say we want to measure this point of the V. This one represents V and this one represents S. The more we move from the 0 point, from the origin point, the less V it will be because it is a flipped thing. You understood? Hello. The same thing for the substrate. The more we move there, the less of it. The closer to the origin, the more of it. Hello? Now, X is a changeable factor. This one, the more substrate you put, so it's a changeable factor. Depending on that, we will get the velocity. Now these two, M, the slope, it is Km over V max. This you have to know by heart. M, it is Km over V max. Good? Hello. Now, this one is the slope. Tamam? Y-axis intercepts the point that the graph, the red line, cut this line. This is what? This is 1 over V max, which is this one. It is B. B is the y-intercept, y-axis intercept, it is 1 over Vmax. Hello? Good? Any question? Hello. From this we can flip it. If we want to calculate Vmax, we can take 1 over x, 1 over y. Just to flip. This one, b or y equal 1 over Vmax. Vmax is equal 1, just like, imagine this one is here, flip these two. خلصنا. Good?
Yes.
Hello. This one is the x, the point that the graph cuts in the x-axis. It is what? It is minus km, minus 1 over km. It is not present in the equation, but you can know it from the graph. Hello? It is minus because it is backward here, before the 0. So it is minus 1 over km. Hello? Instead of minus km. It is minus km. You didn't know, yeah, you didn't understand.
No,
Hello. The same thing, we can just flip it and just get km. These you have to memorize. This is the fourth thing, multi-substrate reaction. Multi-substrate reaction are just simply, most enzymes in the body don't work with just one substrate, sometimes two. And these two don't form only one product, they form two. Hello? So they often handle two or more substrates that interact with the enzyme at the same time. Sorry for the, it's misleading. A and B turn into C and D. Easy as that. Hello? Moving on. Now why it is important? Most important reaction such as oxidation reduction reaction follow this mechanism. Two things moving and then we have the products. Now it have type, it have sequential and double displacement. Sequential have two, order and random. Let's start with the sequential. Sequential, what is it? It says that both substrate must bind to the enzyme at first. Hello? Before any product came out. You have this is the enzyme, both of the substrate, you have two different enzymes. First, both of them, they have to be bound. And then we release the product. This is sequential. Now, the difference between ordered and random is the order that the two substrates bound to the enzymes. The ordered one, vending machine, you have to put money and pick. So both and then you have and then the vending machine will give you food. So you put first both of the substrate first. Hello? This is ordered. You order from a vending machine. Both substrate must bind and then we get the product as also in a specific order. For the random, no, it is just like a sandwich. You will make the sandwich and then you will eat it. Making the sandwich, you don't need to be A over B or B over A. خلاص, put everything. بعدين you eat it. After that you eat it. Hello? So sequential, both substrate must bind first, then the products. Double displacement, it is not. You can have one substrate bind, then product. Second one bind, then product. Bing bong, sorry. It is a bing bong. First shot, then product. Second shot, then product.
So is this like an intermediate or does it like...
No, there's no intermediate. It is two substrate, but it is moving. You will have two substrate and two product. First one will get in the enzyme and then get the result or the product. Second one will get and then it will get the product. Instead of them just binding first. I know this is the only difference. Moving on, now we start with something called enzyme inhibition. Hello? Enzyme inhibition, we will talk about overview, types, kinetic, allosteric, very fast. Now for an overview, this is the most part where a student get confused in it. Basically, enzyme inhibition, it says what? It says slowing or stopping the enzyme velocity. body use it to regulate metabolism in order. Sometimes the enzyme is working, خلاص it is not working all of the time, stop it. Hello, and then continue after. So slowing down the reaction or stopping down the reaction. It is used in clinical therapies. This you can just have a look on it. It is the same. See, this is the graph or the speed without an inhibitor. This one with an inhibitor. Good. So it is less speed up to the point where it stops. Moving on, we have types. We have mainly two types: reversible and irreversible. Reversible is what we have a substance that inhibits. This is what we call it. We call it inhibitor. Hello, bind to the enzyme. If it bind and then deattach, this is reversible. If it bind وخلاص it is still bound, this is irreversible. Good. For reversible, we have three subdivisions. We have competitive, non-competitive, and uncompetitive. Hello. Now I have made a small comic story. This one was introduced to us by our senior, so all credit goes to them. Competitive, you have this enzyme, hello, and one day it was with his substrate, hello, it is a friend. Now, one day inhibitor shows up. Inhibitor looks exactly as the same as the substrate. Enzyme is now confused. He don't know which one is one. Hello. So what? You have this. The two compete. Hello. They fight over. Who will get to bind with the enzyme? Who wins? The inhibitor wins, and the inhibitor bind with the enzyme. Now, what the actual substrate will do? He will get angry. He will get furious. Hello. What he will do? He basically go cry to his father. Hello. So he says, father, they mobbed you with the floor. His father says what? Okay, leave it to me. He calls everyone he knows, sister, family, brother, So all of them now gather around the enzyme and the substrate. Now the inhibitor and the enzyme. Inhibitor now is scared. Substrate is again bound with the enzyme. Good. So now first part, which is competitive, the inhibitor and the substrate, they compete. Hello, for who will get bind to the enzyme. Tamam. Upon that, who will win? First the inhibitor, and it will bind. Then substrate concentration will go up. It will remove the inhibitor and then get back. Good. So first, the competitive, which molecule bind first? The E or ES complex. We said the inhibitor want to bind first. So he bound to the enzyme just. He didn't let the substrate bind. So there were no ES complex. And other than that, we have mechanism. So if the substrate bound, this one we get. Hello? If the inhibitor, this one we will get. And then the reaction is stopped. Good? Now, until what? Until the substrate concentration rise and remove the inhibitor and then bind again. Now, this is an image. Hello? Same thing. This is the same exact thing. So this one is the enzyme substrate. This is the normal equation. When an inhibitor, it will. This one is the enzyme inhibitor complex. Hello? It formed after the enzyme bound after the inhibitor bind with the enzymes. This one you can skip. It is just like extra information. The same thing about the constant. For everything you have a constant. For inhibitor, for line waiver, for everything. But you don't need to memorize. Only the equation I just mentioned you have to memorize. Now for reversible, this is the same. This one is an important topic. This one, what we will see after the inhibitor, the competitive inhibitor bound to the enzyme. This one, what we will see on the graph. Hello? So this one is the uninhibited, and this one is the inhibited with competitive inhibitor. What's the difference? Hello? First, inhibitor prevents substrate binding. So what we say, that the inhibitor moved and bound with the substrate. Km is high. Hello? Why it is high? Because substrate cannot, affinity cannot bind with the enzyme. So we said Km is a bad guy, so it went up. For the Vmax, it is the same. Hello? This one is Vmax. Let me just show you. This one is the Vmax. You see the graphs, it is on the same line. And for the Km, we said what? We said the closer to the, sorry, not the closer. This one is a line waiver or Michael. Hello. So it is normal condition. More is like farther away. So this one is the inhibitor, it is farther. Hello? So we what? Km increased. Vmax, same. After we change it into line waiver, this is the origin. We say same Vmax, same point. High Km. High Km should be, this is the Km and this is the Vmax. High Km, so it should be closer to the origin. You can see it moving like this. Hello? Now we will move on to this one is just an equation with something called A. This is just basically, they included the inhibitor and some calculation. This is not important, just like even if you have a look on it, that's enough. Hello? Example in the book, it is succinate dehydrogenase, which converts succinate to fumarate. This one you have to know. What is the inhibitor that disrupt this and won't let fumarate produced? Malonate. Hello? This is a classical competitive inhibition. We now move to the second type of inhibitors, non-competitive. Hello? Hello. Non-competitive, basically you see this image, mashallah, and he is a hard-working man who is trying to move this stone up. Imagine what? Imagine if it was 2 stone. The harder it will get, right? So here basically, I want you have to remember this, a mnemonic. N-O-N, none. So we have 2 things bound to the enzyme. Hello? The substrate is bound. In the competitive, the inhibitor didn't let the substrate bound. And the non-competitive, the inhibitor let the substrate bind because there is another site on the enzyme that the inhibitor bound. Good? So we have what now? This is the enzyme. We have the substrate bound and the inhibitor bound. N-O-N. None. This is basically just the explanation. Inhibitor binds to another site on the enzyme, not the active site. Therefore, it is not competing with the substrate. This one, it can bind also on the active site. In that case, it will bind to E. And if it was the general normal condition where it binds to another site, hello, this is it will be ES because the substrate bound. So both of them. Hello? Sometimes it is just the enzyme have 2 sites and he bind to the substrate. This is the first one. If he bound to the other, he let the substrate bound. This one formed. So it will be ESI. Here you can see it. EIS, sorry. So all of them are compound. All of them are bound. Good? But then he inhibit the reaction. Basic image, this is the normal one. This is the non-competitive. It is the same idea as allosteric. Hello? We move on, non-competitive. This is what? No. Non-competitive have 2 types. Have pure and have mixed. Tamam? What the difference between them? Well, the enzyme, if he wanted to equally bind to the E and the ES, this is we call it pure. If the enzyme bind unequally, sometime E, sometime ES, this is mixed. Here, I have a mnemonic, so I can remember it easily. Actually, this is the graph. Hello, this is the general graph here. And in that one, we had the same Vmax. صح ولا لا? Now, it is not. It is harder. You remember the image? Hello, with the 2 stones? It is harder for the enzyme. Therefore, the velocity is decreased. تمام. The velocity is like the good thing that you want. The more it is harder for the enzyme to work faster. Hello, but in the Km it is the same Km. Hello, this one follow the pure. You have to remember this one is the line waiver. Hello, and this one is the mixed, the graph for the mixed. Sorry. Yes. طبعا I know it's a little bit confusing to see it at first. Pure competitive. Pure mean what? Let me just tell you, sorry. Yeah. You see, pure, we say that is equally bound to E and ES. Pure, you can visualize him as a spectator, someone who watch the thing happening away from him. So he doesn't have any hate. Therefore, Km stays the same. Tamam? But because he is not doing anything and he's not interacting with them, the Vmax stays the same. The Vmax decreases. Hello? This is a mnemonic. You have to know that we have two types of non-competitive, pure and mixed. Pure equally to both, mixed unequally. You have to know what is on the graph. Hello? If we have the V in the pure, we have the Vmax decreases, the Km stay the same. A mnemonic for this is just a guy, a spectator who watch from away. Hello? So what? He doesn't do anything bad to them. Hello? And he does. He is an inhibitor at the end. But this is a mnemonic. So I represented Km as hate. He watched them from further away. So it is no hate. But he doesn't do anything though, so Vmax decreases. For mixed, you can say it is a picky eater. Hello? Someone who always picks to eat. I don't like this, I don't like this. So what? So the Km, the hate for him, sometimes he likes the food, so it is increasing. Sometimes he dislikes it, so it decreases. Hello? But because he's a picky eater, every time you give him the food, he doesn't like it. So the Vmax is always decreasing. Good? Yes.
So it binds to both like the allosteric site and the active site, or what?
Yes. Both. You have the enzyme, two substances bound to it. The inhibitor and the substrate. خلصنا? Now in the graph, this is what? This is basically you see the Vmax is going away. So it is decreasing. Hello? But the Km is the same. This is for pure. Mixed, the Km, it is moving, the Vmax, it is moving away. So it is decreasing because this is line waiver. And the Km, it is depending. Sometimes it go like this in the black line, increasing. Away, it is decreasing. Good? Okay. Moving on with this one equation, it is just like what the book says. You don't have to actually read it or pay attention to it. Now the third type, which is what? Which is uncompetitive. Hello? Uncompetitive, it is represented as someone who is malicious, khabith. And the first, he is a simple guy, this one, and he let the substrate first bound to the enzyme. Good? And then what? At the end, he is an inhibitor, so he inhibits. Tamam? So uncompetitive, it is what? It is the substrate bind first, it bind only to the ES, and it prevent the reaction from forming the product. You can take a mnemonic. You can take a mnemonic. It is uno, un. It is just like switching. In the first, he's a respectful guy. In the end, he inhibits, so he's not. Good. Now for the uncompetitive graphs, what you have, the Vmax decreases. Hello, the Vmax decreases, but and the Km also decreases. Hello, this is the Km. This is the original one. So it is less. On the line waiver, you can visualize the line going away from the actual one. So both here, it is going there, so it is decreasing. And it is going there, also Km decreasing. Good? Km is always here, Vmax is always here. You have to see in which direction the line moves, apart from the normal one. Hello? This one, it is the same thing. They implemented AA. It is just like counting for the normal equation with the inhibitor. Don't focus on this. Focus on the main one. Hello, enzyme inhibition. This is irreversible. We talked. It's just like the substrate. All of these that we talked about the inhibitor at the end. خلاص, move away from the enzyme. Irreversible, لا. He bound to the enzyme and stick with it and destroy it. خلاص, enzyme can't work. Good. Moving on, we have this is just you can see the bond type. Reversible, it is weak, so deattach. Irreversible, it is strong, sticks with it. This one is what? This one is the all of we talked about. I made a board so you can visualize things. You have to remember competitive increase on Km, on Vmax. It does not, it is the same. You have to remember this. Hello? And these are the graphs. Now we move to allosteric enzyme. What are they? Basically, we talked about them. It is enzyme with another site, something bind to this another site, either activated or deactivated. Good? That's it. But in the graph, it shows only sigmoidal. Hello, you asked. Only sigmoidal because what? Because once one substrate bind, others will start only to bind. He say only, oh, this one bound. Let me go with him as a team. Hello? So therefore you see this increase in the graph. Lastly, you have the macromolecular crowding. What is our goal? Hello? It says that when they calculated the enzyme kinetics, they calculated in the lab. In the lab, it doesn't represent what's happening actually in the body. Why? Because in the body, there is a lot of substances that are highly condensed together. Therefore, it is not showing the same exact thing. Also, you say it is a lot of crowding happening in the body. It is bad for the enzyme. It is not. Enzymes like to work in crowded places. Hello? But with deficient, in segments. It is crowded in the body and it's a good thing for the enzymes. That's it. This is in vivo or in lab. This is in vitro, in lab, vivo, human. And this is in the enzymes. Now the last lesson, regulation, very easy lesson. We're going to have 5 things: overview, genetic, covalent modification, allosteric, and compartmentation. For an overview, hello, we want to regulate things. صح ولا لا? So what? We keep things calm and balanced. You see the dot. We need it to control and regulate the enzymes. Why? We want to maintain the order. Everything is organized. Everything is stable. We want to save the energy. The enzyme work only when there is something needed. Hello? And react to changes. Something outside happening. We have to do something to fix this problem. So we only work when we need it. Hello? We react to outside, and upon that we work in the way that save energy. Good? Hello. Now, how do we keep the enzymes regulated? 4 things. It is genetic control, covalent, allosteric, and compartmentation. First one is genetic control. It is basically what? It is regulating the genes. Now, in the DNA level, you make the enzymes. صح؟ لأنه enzymes are protein, and from the genes you make the proteins. So we want to go there and خلاص. We tell the specific gene make this enzyme. The cell make the enzymes only when needed by turning the genes either on or off. Hello? Example in the book they used E. coli. Hello? E. coli in the body, it don't have the enzyme lactase. Hello? E. coli is a bacteria in the digestive system. It don't break lactose. So why? Because it don't have lactase. This is the enzyme. Hello? This is the enzymes. What it say? When lactose enter the body, it will bind to something that's blocking the gene and then move it away. Gene is now free. It make the lactase. Lactase break the lactose, the first one. Hello? Just know this simply. Moving on with covalent modification. It is what? It is basically the enzymes can be switched on and off. Hello, by what? By either adding something or removing something. These things usually are small chemical groups. This is the process that we have. We have phosphorylation, adding BO4. Hello? And we have methylation and acetylation and nucleotidation. Basically, just know them. And then the phosphorylation, it is the most common. The mechanism, it is what? ATP. ATP is something you will learn. Hello? Or you have learned it in the chapter 4, right? But this is ATP. The last one, it is B, phosphor. So the phosphor, it donates the phosphor to the enzyme. Enzyme bind to the phosphor, covalent, hello, and then work. That's it. How it works, the mechanism, the BO4 or the phosphor group, it bind to the OH of, in the active site, we have either serine, threonine, or tyrosine. These three have OH. BO4 from the ATP bind to them. Now we have a covalent modification of the enzyme. Enzyme, substrate. These three have OH. BO4 bind to them. Now enzyme is activated. Hello? This is an example of the thing. These follow the same, it is the same processes, but not of these enzymes. You have to know this. Hello? I made a mnemonic. SIFTI. S-F-TI. Good? Moving on with this is what it's basically something called zymogenes or proenzymes. Enzymes made, when they are made, they are inactive. They want someone to modify them. We can cut some parts of the enzymes. Upon that, it will work. Same thing. So we remove some parts from the enzyme. This will make it work. Allosteric regulation, we talked about it. Hello? Enzymes, substance bound, either activate or deactivate. This is the graph you see. Now, why it happened, or basically types of effector, you have two. You have homotropic and heterotropic. Homotropic, that's something that bound to the enzyme, it was the actual substrate. Hello? So substrate of the enzyme start the change. But for heterotropic, something else, another substances start the change of the regulation. Hello? Enzymes are multi-subunit proteins. Enzymes like let's say a big structure made of different parts. Upon these parts, how they change from the inactive to the active, we have two models. We have the concerted and we have the sequential. For the concerted, all subunits switch together. Hello? All the subunits, this is an enzyme. These parts are inactive. Something bind to it, make it active. Now, it is these both, when that substance bound, both of them at the same time converted to the active side, active version. The active one, we call it R, relaxed. You see, when you are relaxed, you can work and you be active. When you are tense, hello? When you are tense, you can't work really. So you are inactive. Good? For the sequential, the same thing happened. We are moving from inactive to active, but in a stepwise reaction. So only something bind, one part of the subunit change, and then the others move on. Not at the same time, but at the end we will move from the inactive to the active. Compartmentation is just what it is, as we said, inside of the body, there's a lot of things that are working, right? It is highly condensed. So we don't want things to be messed up. So we have compartment or segments that divide everything of the cell. This part works alone. This part works alone with its enzyme. And this part works alone with its enzyme. Hello? Why do we do it? For four things. because we want to divide and control. We want to keep the different reactions separated from each other. And some reactions produce waste. We don't want this waste to interfere with other reactions. Hello? Second thing, we have specialized reaction conditions. We say that enzymes work in different conditions. Some enzymes want like a high pH, some want low. So we want to have different part for them. Damage control. It is some reaction in the body are toxic and dangerous, but should be happen. So we move them to other place so they don't damage the other tissue. The last thing is diffusion barrier. It is basically the inside of the body is crowded, as we say. So the enzymes need to move a little bit. So what happened? Imagine if all of them are crowded, the enzyme won't work correctly. So we have a little bit of let's say pathways, or in between the segments, the enzymes can move from one department to other department, like making a road for them. And that's it.